Does a latch consist of two flip-flops? No. A flip-flop consists of two latches. A latch is edge-triggered clock. No. No, it is not. A latch doesn't have a clock on it. It's not a clock. Anyways, does this oscillate? No. In order for something to oscillate, there must be an odd number of resistors in this loop. This loop. So if there was like a third one like right here, then yes, it would oscillate. But no. No, it does not. This does not count since it's outside of the loop. Does this oscillate? No. In the more sequential circuits, outputs of the circuit is a function of inputs. In a more, the output of the circuit is a function. The output in a more circuit is a function of the state. Like 0, 0 slash, and you'll have the output in there. The 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 the, the inputs are a function by themselves, right? This is false. I'm right. In a finite state machine, FSM does using D flip-flops. Inputs D are the next state's Q plus. So using D flip-flops, inputs to the flip-flop are the next state. Yes. On the excitation table, D is equal to Q plus. True. In a T flip-flop, when T is 0, false. 0 is hold for the T flip-flop. In an SR flip-flop, the pattern SR equals to 1 1 causes. No, you cannot have 1 1 on the SR is illegal. You can't do that. Rising edge clock flip-flop output Q changes rising edge. So when it changes from 0 to 1, 1 to 0, false. Okay, so for this, it's a counter. So despite there being 5 states, you would say 3 flip-flops? No. No. For the counter, you need to also be able to count to the numbers in the states. 11, which in 3 bits, you cannot get to 11. You can only get to 7. You need to get to 11, which you need a 4th flip-flop for. So, FSM design is of 9 states. Then the number of flip-flops needed to implement the circuit is 4. Um, because 4 raised to the second power is 16. 3 to the second power is only 8. And that's not enough, so you need 4. Counter is initialized as 0, 0, 0 and counts the following sequence. And this counter is said to be, I got this right on the exam, it's D. Mod 3. Mod 3 are the counters. The circuit above in part 11 requires 1, 2, 3, 4. I would have said 2, but it's 4. You know why? Because it counts to 10. I wonder what I picked. 12 is B. Like, how do I get this one right? But I got this one wrong, which is the exact same thing. Like, I missed that. Oh my gosh. Oh, that's actually infuriating. That is actually infuriating. Alright, if Q is initialized to 1, then when the clock is triggered, Q plus is 0. So Q, the next state of Q, um, well, T is a function of Q bar in this state. So if Q is initially 1, right, this is 1, this is 0. So 0 coming through gets inverted here to a 1. T is a 1, that's toggle. So Q becomes a 0. So the next state of Q is 0. That is true. T is equal to 0 always. Oh, I'm for this. No, T will eventually, like if you do it again, well, in the next state, right? Q becomes 0. This is 0. Now this is 1, right? Right? This is 1 now. So 1 coming through gets negated. T is now a 0. That is hold. So, um, is T always 0? No, it's going to be alternating. So it is not always that. The flip-flop is positive edge. Well, there's a little bubble here. So no, it is falling edge. So that's false. Alrighty. So for this diagram here, you're going to use the excitation table. D is, a function of the next state, right? But this is a rising edge. So you're not going to be doing D. Q is going to follow the value of D, right? So whatever D is, like you're given D in the clock, we have to draw Q. So D is given. So whenever D is a 1 or a 0, whenever it's these rising edges here, right? These rising edges, whatever those are, it's going to initially, like whatever D value is, it's going to copy that until the next rising edge, right? So, and it does that. Here, it's a 1 initially. It's a 1 again here. It's a 1 again. It becomes 0 here. D is 0 here. So it goes down, right? Another rising edge. D is still 0 here. It's still 0. There's a bunch of scribbling, but, whatever. T. For T, whenever T is a 1, it switches the value of Q. And whenever T is 0, it holds the value of whatever Q was previously. So that's how you're going to solve that. Um, So for this part, where this is aperture time, it's looking at it, it's like the setup time is 2, the hold time is 2. So the setup time is before, right, 2 nanoseconds. So what is this, rising edge? Setup time is 1, 2 nanoseconds, so it's here, right? That doesn't seem too right. So the hold time is here, right? Well, D in the clock, right? They ain't looking too right. It's violating the setup time here. This is the setup time. And then after the clock is the hold time. So D is obviously too close to the rising edge, right? Or this value switch. Can't have that. That is not good. It violates the holding time setup, which has a setup time of 2 nanoseconds. It's not, the D is changing within those 2 nanoseconds. You can't have that. It needs to keep a constant value. So yeah. Consider the circuit shown, X and Z, the output Q is initialized to 0. Okay, initially Q is 0. Got a D flip-flop. Right? So, is this a mealy or more? Let's see. X here is a function of the output Z. So it is a mealy, right? Now, how would you fill out this state table? Well, you'd first go to X, right? And Q, right? So present state, right, for Q, we can have X be a 0, or we could have, uh, let me go to my test real quick, make sure what is given to us for this question. And we are given X and the present state. Okay. And we fill it out. So we have X and Q are given, right? So how do we fill up D? So if X is Q, well, if X and Q is initially 0, and what if X is initially 0? So you have these are just a bunch of combinations, for X and Q to try out. So if they're both a 0, well, D is also a function of Q bar. So it's also OR gate. So if Q is 0, well the state, well Q is, what D is equal to, right? D, the Boolean algebra is X plus, which is OR, Q bar. So if Q, whenever Q is a 0 in this statement, D is a 1, then you write the Boolean algebra for Z. Z is Q bar exclusive or X, right? And then Q bar is just the inverse of whatever. And the next state of Q is a function of D. That's always been true for the D or D flip-flop. So you will use those to fill out that state table. Right, you use that Boolean algebra to plug in values and see what the outcome is, and give the state diagram based on that. So for the present state being Q, it can either be a 0 or a 1. There's only two states, funny enough, and two possibilities for either. Well, there's actually one, two arrows going to 1 and two arrows out of 1. There can only be two different possibilities for each state. So, alright, if the input, if the sequence 0, 1, 0, 1 is applied, where 0 enters the circuit first, and circuit is initialized to 0, what will the final values of Z and Q be? So 0, you get a 0 coming in. Oops. You get a 0 coming into this. We're using this for this question, this state table up here. Alright. So you get a 0. Alright. So when you get a 0, when you're starting at 0, the first state, you go to 1. Then you get a 1. You go to 1. You get a 0. You go to 0. You get a 1. Your next state is 1. So this is Q, or the states. Z being the outputs is equal to whatever outputs there were. So 1, 0, no. The first one being a 0, so the output's a 1. And the next one being a 1, it's a 1, 0, 0. And that's that. Alright, how you do this? Well, despite the question asking find the minimum cycle time, which confused the fuck out of me, TC, this formula is equal to 1 over T minimum, which is the minimum cycle time, right? So no matter what, I guess no matter what the question is, when it says minimum cycle time, it's referring to the picoseconds when you're calculating the maximum frequency for the circuit. So that confused the fuck out of me. So TC equal to, let me remember, TPCQ plus TPD plus T setup. And you'll take the longest path, which is, we'll find that there's 1, 1, 2, 3, 4. 4 is the highest. 1, 1, 2, 3. 1, 1, 2, 3. 1, 1, 2. 4 is the highest, which is this route. That one. And that'll correlate to the PD time, and PCQ and T setup are given. So That'll be straightforward. Is there a hold time constraint? Yes. Hold time constraint has to do with the shortest path, which is here. And if the T hold is less, or if the hold is greater than the setup, um, or no, if the hold is greater than the TCCQ and the TCD, then you have a hold time violation, right? So the formula T hold TCCQ plus TCD. TCD refers to going through gates and whatnot, but for that single wire down here, there are no gates. And CCQ referring to contamination delay um, is 15. So T hold has a value of 25. 25 is greater than 15. So you have a hold time constraint there. And to correct that, you would add a buffer to all the circuits in the diagram, right? You would add it to everywhere at the beginning of each flip-flop. I would say it would be a better choice here at the beginning here so that all the circuits get that buffer. And you want that so like no other circuit ends up becoming like an equal amount of buffers so that the whole path doesn't change. So yeah, that concludes this little review session, for the homework exam.